Okay, so picking up where we left off, so what I'm saying here is that to do this design, you have the positions, the angles, and the orientations that you need the grabber to be in. Um, if in terms of them all being lined up right over each other, so kind of the base would be in the same position no matter where you're picking up. The problem with that is that one of the pivots is way off the robot, and so what you can do then is because you are free to move the robot into a different distance back from the plate, depending on which one you're picking up, you have that degree of freedom. So now you can just you can try, so you can easily just move these back and forth, see where the pivot points would be, and you can move. So this one is fixed. We fixed that one. We can move this one. And so you can see what would be nice is if you can get these in a position where you have, you don't have really long links. And then, of course, you have to do your force and torque analysis and make sure that the link that you're going to be able to drive doesn't going to have some really big torque requirement. So you kind of have to do an iterative process, weigh all these things together, and come up with, something that has has high enough transmission angles, and and the pivots are in a reasonably convenient place on the robot. So again, just to review what we did here, we created the outline of a grabber, and we put that in the three different heights and angles that it had to be at. This one was fixed. We put enough constraints on here to maintain the angle and the shape, but we can drag it, to the left, to the right. The same thing with the bottom one, until we come up with what looks like reasonable positions, distances, and we'll have to check the torques. And so for this case, there's a pivot point there and a pivot point there. And so then we can just build the robot around that with those supports in that particular place. So let me just turn on the robot. Okay, so now you can see there's one pivot point right there, and there's another pivot point right there. And so this allowed me to figure out where to put the pivots, and then also how long the this pivot right here is going to connect to the bottom, right? And this pivot right here is going to connect to the top. Okay, so you can see now the rest of the robot is filled in. Here's the pivot. Here's down to the original corner, the grabber. Here's this pivot coming over to this point. So basically just built the robot around those positions, and then figured that we would likely need a two-stage reduction. So these are actually 5-inch pitch diameter, 1-inch pitch diameter, 2 stages. The gear profile of this link is actually built right into the link itself. So in other words, it doesn't have a separate gear. It just you could 3D print or laser cut or whatever the teeth right into the link itself. And so once you have your model, of course, you can turn on things like you can have SOLIDWORKS show you where the center of mass is of the different parts. You can take the whole assembly and have it calculate the center of mass of the whole assembly. And of course, you want to make sure that the center of mass, when you're reaching out with that plate, that the center of mass is behind this wheel so that you don't tip over. And then you can actually have it run. I'm just going to turn those symbols off there. Then you can actually run a motion analysis study on it. And so if you do that, you can see that this is the torque required to drive this link right here. And you can see that it starts out negative, which makes sense because you're trying to twist this clockwise. If the right-hand rule, that'd be negative. As it reaches out, right, it goes up, and then eventually when you get over past this point, now you actually need to keep it at steady state or steady motion without accelerating. You have to apply a back torque to it once you get past a certain point. So that's pretty useful.